In this video, we'll learn how to test a hypothesis regarding two populations. First, we'll look at population proportions, and then we'll look at population mean. So let's start with the first question, which is the happiness question. Generally, how would you say things are these days in your life? Would you say that you are very happy, pretty happy, or not too happy? So each person in the survey responded to this question. Given this, we can actually compare the gender difference in terms of happiness. In other words, we can look at, are men happier than women or vice versa. So in this case, we have two groups or two populations. One is male, the other is female. And we want to see the difference between these two groups in terms of happiness. So to measure this difference, we actually want to look at this in terms of the proportion. So in other words, we want to compare the proportion of very happy people in both groups. So suppose if men has a higher proportion of happy people in the whole male group than compared to the female group, then that means men are generally happier than women. So that's that's the idea of testing the hypothesis in terms of proportion. So we can compare the difference between two groups in terms of proportion. So let's see how we can do this in R. To do this, we need to first find out the contingency distribution of happiness in terms of gender. So here we can create a contingency table for those two variables. So we have a table function for both variable Q1, which is actually the happiness question, and also for the sex variable, which is the gender. So we create a table for both variables, and we call the table happiness underscore sex. So that's the name for the table, which is we will create in R. So let's run this line, and you can see nothing really happens in the console. To actually see the results, we have to type in the name of the table to see actually the actual distribution. So you can see here now we have a distribution in terms of those two variables. So the row here, the row variable corresponds to the first variable. So here we have option 1, 2, 3, and that's for the happiness question. So we're very happy for 1, pretty happy for 2, and not too happy for 3. And similarly, we have the column variable corresponds to the second variable here in the table function. And then that's the two genders. So 1 is for male and 2 is for female. And given those two variables, we can see the distribution here. So for male subjects choose very happy, and 7 male subjects choose pretty happy, and only 2 choose not too happy. On the other hand, for female group, so 8 choose very happy, and another 8 choose pretty happy, and 1 female subject choose not too happy. So that's the distribution in our sample in terms of happiness and gender. To visually see this or to compare the difference, we can actually create a bar plot for the distribution. So here we are creating a bar plot for the happiness underscore sex. So we want to create a bar plot for this contingency distribution here. And let me run the bar plot first, and then I will explain the code, what each part of the code does in terms of creating the bar plot. So let's run the whole line here. And you can see now here is a bar plot. And here we have actually two bar plots. One is for male group, and the other is for female group. And actually that's what the beside function or parameter specifies. So you can see here, so in the code we have beside equals to true. So that means we are actually creating two groups, and we're placing the bar plots for those two groups beside each other. And first the first bar plot, the first part will correspond to the first column in the matrix, in the contingency distribution. And then the second bar plot here for female will correspond to the second column in the contingency distribution. So that's, and then we plot those two bar plots beside each other. So that's the beside function parameter here. And then we learned that men equals to overall happiness these days is corresponding to the title here. And we have the names arg or names argument parameter, and then it's combining male and female. So that's the that's specifying the arguments for the or the label for each group. So one is for male, the other is for female. And here, one thing that we have extra in this bar plot is the legend. So in order to know which bar represents which option, then we have to specify, we have to put a legend here under the plot. So that's where we have this part. So legend dot text equals to true. So we're basically saying that, okay, so now we're adding a legend box to the bar plot. And here the args dot legend basically is the legend parameters. So now we're putting all the parameters into the same list. So here we have a list. You see that specifies all the parameters for the legend. And the first two are the location parameters. So we have x equals to 8 and y equals to -1. So basically that specifies the location of the legend box. So x equals to 8 is basically saying that, okay, so now the center of the box in terms of the x-axis is around 8. So you can see here, so if we look at this plot in horizontally, then the center of the box is around 8. So that's where the 8 is. And then y equals to -1, basically that means the vertical location of the legend box will be -1. So that you can see it's below 0. So that's -1. And then we have the legend itself equals to very happy, pretty happy, and not too happy. So that will be specifying which group it is for the legend. And then we have nco equals to 3. Basically that is specifying how many columns we want to have in the legend box. So we have 3 columns here, so but we'll have 1 row. So that's specifying the structure of the legend. And given this whole list, then basically we can change the parameters for the legend only. So that's one parameter or one element for the whole legend specification. So if we run the whole line, then we get this plot. And then it tells us the difference between male and female in terms of their happiness. So it looks like from the graph that male are less happy than female, right? So you can see I mean, proportionally speaking, there are more female group that are very happy and pretty happy. But I think because we have less actually male group, I mean male subjects, so this bars looks smaller. But now we want to see whether the difference is statistically significant or not. So in other words, we want to see whether statistically speaking, male are less happy than female. And to do this, we want to carry out a hypothesis testing in terms of the proportion of male and female who are very happy. So we use the proportion of very happy individuals in the group as a measure of the happiness. So if male group have a higher proportion of very happy people, that means male are happier. If it is true for the female group, then that means female group will be happier. So let's see if there's any statistical difference between these two groups in terms of happiness, or in terms of proportion of very happy people. So now we're essentially testing the proportions here. So we carry out this test by using the proportion test function in R. So that's a prop dot test function, and then we specify the parameters here. So you can see the first is C for 8. So that's the two axes here. So 4 and 8 are x1 and x2. So that's the number of individuals with a desired characteristic in each group. And we know that in male group there are 4 people choose. You can see there are 4 people choose very happy. That's in the male group, and there are 8 people in the female group choose very happy. So we want to see. So we need to specify the x1 and x2 here first, and then we specify the sample size. So we have 13 male subjects and then 17 female subjects, and then basically R will calculate the proportion by itself. So that'll be 4 over 13. That'll be the proportion of male who are very happy, and 8 over 17 would be the proportion of female who are very happy. And then we can specify the other parameters as correct equals to false. So that's the continuity correction equals to false. And then confidence level equals to 0.9. So we're using a 90% confidence level or 10% significance level. And we're using a left tail test because we're testing whether male are less happy than female or not. You can see because in the graph it looks like that male are less happy than female because there are only 4 male choosing very happy, and there are 8 choosing very happy in the female group. So we want to see whether it's actually true that male are less happy than female. So that's a left tail test, and we specify the alternative parameter equal to less. So let's run this and see if we have statistical evidence showing that male are less happy. And you can see here, so here are the results. So we look at the result from the p-value. So p-value equals to 0.1834, so that's about 18%. In other words, that is more than 10%, right? So we know the significance level is 10%. So the p-value is actually greater than the significance level, so we would not be able to reject the null hypothesis. Actually, then we will say that there's actually no sample evidence suggesting that male are less happy. I think probably here the reason for this non-rejection is probably because we have a small sample. And you can see that we have the sample proportion estimate. So for male group it's actually about 30%, for female group is about 47%. If you look at the sample estimates, female group have a larger proportion, so it looks like that female are happier. But because of the sample size is small, so we would not be able to reject there's actually statistical difference between those two groups. So that's how we can test two population proportions using R. And then now let's move on to means. So we can also test two means. In this case, we want to look at a different example. So that'll be the question 30. So let's go to question 30. We will look at the mean case in two different ways. So one is one is for dependent sample, and the other is for independent sample. And we'll look at the dependent sample first. So here is question 30. And you can see here, so question 30 basically asks people about different characteristics of a job. And then they ask people to rate the importance of different aspects. So we can see here, so we have a few aspects. So having a high paying job, having job security, being able to make time to take time off for family and childcare needs, and having a job you enjoy doing, so and so on and so forth. So we have different aspects of having a job, and then people rated the importance uh, in terms of each aspect. So for suppose for option A, having a high-paying job, is that extremely important? Is that very important? Is that somewhat important? Is that not too important? Or is that not at all important? So people can rate on a scale of 1 through 5 to kind of determine the importance of a certain aspect. And then given this question, or given the results to this question, we can actually compare the average importance, right? So then we can look at how comparing having a high-paying job and having a job that you actually enjoy doing, which is actually more important, right? So if people have an average rating, importance rating, which is higher than which is higher for high-paying job than having a job you enjoy doing, then that kind of tells us, okay, so high-paying job is more important for people. On the other hand, if people rate having a job that they enjoy, if their rating is higher for this option compared to having a high-paying job, then that means people think they need an enjoying job, not a high-paying job, right? So we can compare the mean average, the average importance level to see which aspect is more important to people. So to do this, we need to carry out a t-test, because in this case we're comparing the mean importance level. The mean importance level is basically the average of the importance level people specified in the dataset. Actually, let me show you the raw data in the spreadsheet, and then you will see kind of the idea of having the averages here. So we have question 30A, 30B, 30C here. So you can see here, so each person have a rating in terms of 1 through 5. So 1 is extremely important, and 2 is like very important, and then the list goes down in terms of, as we increase numbers, the importance actually goes down. So 1 is the most important, extremely important. So if we want to compare a high-paying job with a job that people actually enjoy doing, so we are basically calculating the average of all the importance ratings for the first option, or the A option, with the average level of importance level for the D option. So we're comparing two averages here. And to actually test this in R, we use the t-test. So we have the t-test for dependent sample in this case, because each person gives a rating for part A and part B. So the answer for part A actually depends on the answer is dependent on the answer of A, because they come from the same person. So we have a dependent sample in this case. And to test them, so we're comparing two means. One is a mean from question 30D, and then the other is from question 30A. So that's specifying the two columns of data from which we are calculating the mean. And then we have the paired parameter. So that equals true means it's a dependent sample. And we choose the confidence level as 95%, or in other words, the significance level is 5%, and its alternative equals to less. In other words, we're saying that option D is less than option A. There's a caveat here. So because we know the importance level goes goes down as we increase the number. So numerically, if a number is less than another number, then that number is actually more important. So the last number is more important because we think, okay, so if we're looking at whether having a job that people enjoy is more important than a high-paying job, then that means the number from 30D, which is a job that they enjoy, should be less than the high-paying number. So that's why we have a less um, here in the alternative parameter. So let's run this and see if we have a significant difference between the two options. So by looking at the p-value, actually it's a very small number. So that's 1 like 0.00001. So that's 1 to the negative 10 1 times 10 to the negative 4th power. So that's a very small number. So in this case, we actually can reject the null hypothesis. If we're rejecting the null hypothesis, that means actually there is a big difference or statistical significance, a significant difference between having a high paying job and having a job that people enjoy. So in this case, we actually see that so the number for question D is less than the rating for question A. I mean that means the importance for D is actually is higher than A. So we do see that there's people think having a job that they enjoy is more important than having a job that pays a lot of money. So that's what the data tells us, and it's statistical significant. And lastly, we can also test the means for independent samples. So in this case, we would so we can still use this example, but we can look at the difference in terms of the gender. So in this case, we would have so suppose we want to look at the gender difference in terms of let me see, the gender difference in terms of the high-paying job. In other words, whether between male and female, which group thinks having a high-paying job is more important. So it might be that if male thinks having a high-paying job is more important, then their average rating will be a less number. And if women thinks having a high-paying job is very important, then that means their female would have a less number. So then basically we want to see which group have a less average rating for the option A here. So that's the idea to test hypothesis regarding two population means. So I have two populations, the male and female, and I want to see what's the difference between their average their mean ratings of the option A. Actually, to see this a little bit more clearly, we can look at the mean first. So here I have this code. So that's the mean function, and we're looking at the number, the response for 30A. So that's the high-paying option question. And then we want to specify the male group and the female group. So you can see here, so we have a bracket here. So bracket means we're subsetting the data or the column here. So we have one column. So we have one column here for 38. So this column theta includes both male and female. In order to test the gender difference, we want to separate them first. So we want to separate the answers for male and from the answers for female. So that's what we're trying to do here. So we have a subsetting bracket that subsets the data which satisfy this condition. So which data, sex equals to 1. So we're saying that, so if this which function is true, meaning that data equals to 1, then we will pick that data in the subset here. So in this, essentially we're selecting male by using this function, and then after we selected the data, we calculate the average of the numbers. So this part subsets the 38 in terms of the male group, and then we calculate the mean of that group. And again, so na.rm means that we're removing those not available data or missing values. So here we run this line, and we can see that the average rating for the importance of having a high paying job for male would be 2.27. So that's kind of very important, important. Not very important because it's less than 2. 2 is very important, but it's a little bit higher than 2. That means it's a little bit less than very important. And then we can compare this with, look at the mean for female as well. And the number is 2.78. So that's even a larger number. So that means female thinks having a high paying job is actually even less important compared with men. So then, given the sample, it looks like that male or female thinks having a high paying job is less important. But we want to see this statistically. So we'll carry out a t-test by comparing the two means. So one is the first part, data which sex equal to 1. So this is one subset of the 30A column of data, and then here's another subset, the female subset. So we're comparing those two subsets of data, and here paired equals to false means that they're independent samples, right? Because male and female they have nothing to do with each other, so they're independent subjects from the survey. So paired will be false, or we are having independent sample. And again, we choose confidence level equal to 95%. And here we use alternative equals to two-sided, which is looking at which one is actually either different or not. There's no particular direction in terms of the comparison. So let's run this line of code. And from the p-value, we can see that it's about 14%, so 0.1377, and that's much larger than 5%, which is the significance level. So we cannot reject the null hypothesis, and actually, then that means there's not much difference or gender difference in terms of thinking whether a high-paying job is important or not. So we can interpret the results as saying that we don't have enough evidence to show that male are more thinks high-paying job is less important, or vice versa. So that's what the test tells us. But probably, if we have a larger sample, the result might be significant. Or in other words, if we have a larger sample, then we might see a difference between the average importance ratings between male and female. Probably, I guess, male would think high-paying job will be more important, relatively speaking, compared with women. So that's how we can test this hypothesis sigma. So that's it. So we learned how to test the hypotheses regarding two populations in terms of proportion and also mean. For the mean case, we'll look at the dependent sample and also look at the independent sample. So that's this video. Thanks for watching.